The morning of May 6, 1943 at Rechlin-Lärz Aerodrome, approximately 60 miles north of Berlin, Oberst Edgar Petersen stood in the shadows of Hangar 7, arms crossed, watching as his technical team removed canvas coverings from the aircraft they had recovered 3 days earlier from a forced landing near the Dutch coast. The machine before him looked like something that belonged in a museum, not in the middle of a world war. Wooden construction, plywood skin, no defensive armament visible on this variant. It seemed impossible that this relic had been terrorizing German airspace for months. Petersen had commanded fighter units since 1939. He had flown against Polish biplanes, French Marines, and British Spitfires. He understood aircraft construction, performance envelopes, and the basic physics of air combat. Everything Heckner told him that wood was obsolete. The future of aviation was metal-aluminum alloys formed into stressed skin. Monarchs that could handle high speeds and combat stresses. Germany had invested enormous resources into developing advanced metallurgy and precision manufacturing for aircraft production. The Messerschmitt Bf 1009, the Focke-Wulfs 190, the jet-powered Me-262 that was beginning flight trials all represented the pinnacle of modern aviation engineering. And yet this wooden British aircraft, this de Havilland Mosquito, had been making fools of the Luftwaffe for over a year. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Petersen had read the combat reports, mosquitoes photographing Berlin in broad daylight, flying so high and so fast that interceptors couldn't reach them, mosquitoes bombing Gestapo headquarters in Oslo with precision that seemed impossible. Mosquitoes appearing on radar, then vanishing before fighters could scramble. When fighters did intercept, the mosquitoes simply accelerated away. The British called them the Wooden Wonders. German pilots had less charitable names. The aircraft sitting in Hangar 7 was a photo reconnaissance variant. A PRM Merc IV according to the identification plates. The pilot had been forced down by engine trouble, not by German action. He had destroyed what he could before capture, smashing instruments, burning documents, but the airframe was largely intact. This was the first relatively undamaged Mosquito the Luftwaffe had obtained. Every previous capture had been too damaged for meaningful analysis, destroyed by crashes or by their crews before German forces could secure them. Petersen's orders came directly from Reich Marshal Hermann Göring's staff: examine this aircraft. Determine its performance characteristics. Understand why German fighters cannot catch it, provide recommendations for countermeasures. The implication was clear. The Luftwaffe was desperate. They needed answers. As technicians began their inspection, measuring, photographing, and documenting every detail, Petersen walked around the aircraft slowly. The fuselage was smooth, beautifully shaped with elegant lines that suggested speed. The wings were thin, almost delicate-looking. The engines were Rolls-Royce Merlin, the same power plants that drove Spitfires and Lancasters. Nothing exotic, nothing Germany couldn't theoretically match or exceed, but it was made of wood. Petersen reached out and knocked on the fuselage. It produced a hollow sound like tapping in a crate. He had flown metal fighters his entire career. Metal meant strength, durability, modernity. Wood meant biplanes meant the Great War meant obsolescence. The cognitive dissonance was profound. How could this wooden machine outperform the Luftwaffe's finest metal fighters? The question would soon have an answer that would shake German aviation doctrine to its foundations. The de Havilland Mosquito was born from desperation and unorthodox thinking at a moment when Britain needed both. In 1938, as war clouds gathered over Europe, the British Air Ministry was focused on heavy bombers and fighters. The prevailing doctrine emphasized defensive armament for bombers, turrets, gunners, armor plating, all adding weight that reduced speed and altitude performance. Geoffrey de Havilland, founder of the de Havilland Aircraft Company, had a different vision. De Havilland proposed something radical. A bomber so fast it wouldn't need defensive guns. A bomber that could outrun fighters rather than outshow them. A bomber made primarily of wood using Britain's furniture industry and forestry resources rather than competing for the aluminum that was in desperately short supply. The proposal was rejected repeatedly. The Air Ministry wanted heavy bombers like the Stirling and Halifax. They wanted fighters like the Spitfire and Hurricane. They did not want an unarmed wooden aircraft from Designer who seemed to be ignoring modern aviation trends. De Havilland persisted. He had been building aircraft since 1910. His company had produced everything from Tiger Moths to racers to transport aircraft. He understood wood construction intimately. More importantly, he understood that Britain's strategic situation demanded creative solutions. Aluminum production was limited. Skilled metal workers were scarce. But Britain had abundant timber and a vast furniture industry with craftsmen experienced in precision woodworking. A wooden aircraft could be built in facilities that couldn't produce metal planes using workers who couldn't be spared for other aviation projects. In November 1938, de Havilland submitted a formal proposal to the Air Ministry. The specifications seemed impossible. A bomber capable of 415,000 feet powered by two Merlin engines with a range of 1,500 miles carrying a 000 lb bomb load and requiring no defensive armament because it would be too fast to intercept. The proposal was rejected. The Air Ministry called it unrealistic. De Havilland continued advocating for his concept throughout 1939. The war began in September. The Blitz started. Britain was being bombed nightly and the RAF desperately needed aircraft, any aircraft. Finally, in December 1939, the Air Ministry reluctantly authorized a single prototype. They didn't believe in the concept, but they were willing to let de Havilland prove himself wrong at his own company's expense. The prototype took shape at Salisbury Hall, a requisition country house in Hertfordshire where de Havilland set up a design team away from the main factory. Chief designer Ari Bishop led the engineering work. The challenge was enormous. Create an aircraft that could match or exceed fighter performance while carrying bombs using a construction material that most aviation engineers considered obsolete. The solution was laminated wood construction of extraordinary sophistication. The fuselage would be built in two halves, port and starboard, each carved and shaped from multiple layers of wood bonded with adhesive, birch plywood for the inner surfaces, Ecuadorian balsa wood for the core, providing thickness with minimal weight, more birch plywood for the outer skin. The entire sandwich was shaped in massive concrete molds under heat and pressure, creating smooth, strong, aerodynamic shells. The two halves would be joined along the center line, forming a fuselage that was effectively a single piece of molded composite material. The wings used similar construction principles, but with a different structure. Spruce spars provided the main strength members. Plywood ribs created the airfoil shape. The entire assembly was covered with more plywood skin, creating a stressed skin structure where the outer covering contributed to overall strength. The result was remarkably strong for its weight, stronger in some respects than equivalent metal structures because wood's natural fiber orientation could be exploited for maximum strength in critical directions. The adhesive was crucial. De Havilland used a synthetic resin called aerolite developed specifically for aircraft construction. This glue was stronger than the wood itself when properly cured. Joints bonded with aerolite would fail in the wood before they failed at the glue line. The material was also resistant to moisture, fungi, and temperature extremes critical for an aircraft that would operate from Scotland to North Africa from sea level to 30,000 feet. Construction took place in furniture factories across Britain. The bodywork was done by craftsmen from firms like Parker Knoll and Ronson, companies that had been making dining tables and bedroom sets before the war. These men brought precision woodworking skills honed over decades. They could shape complex curves, create perfect joints, and finish surfaces to tolerances measured in thousandths of an inch. Skills that seemed irrelevant to modern warfare suddenly became strategically vital. The prototype first flew on November 25, 1940. Test pilot Jeffrey de Havilland Jr., the designer's son, lifted the aircraft from Hatfield Aerodrome and immediately discovered something remarkable. The plane was fast, extraordinarily fast. Even with the prototype's lower-powered Merlin engines, it reached nearly 400 miles per hour in level flight. It handled beautifully, responsive and stable. It climbed rapidly. Most importantly, it did everything the designer had promised and the Air Ministry had doubted. Performance testing continued through early 1941. The Mosquito proved faster than Spitfires at altitude. It could cruise at speeds that German bombers could only achieve in emergency dives. Range exceeded specifications, handling was benign, making it suitable for average pilots rather than requiring exceptional skill. The wooden construction showed no signs of weakness. If anything, the wood proved more tolerant of combat damage than metal. Bullet holes didn't propagate into structural tears the way cracks could spread in aluminum. The Air Ministry's skepticism evaporated. Orders flooded in. The Mosquito would be built as a bomber, as a reconnaissance aircraft, as a night fighter, as a pathfinder, as a strike fighter, eventually, more than 30 variants serving in roles from submarine hunting to precision attacks on Gestapo headquarters. Production ramped up throughout 1941 and 42, spreading across multiple factories and eventually reaching Canada and Australia. By early 1943, when Oberst Petersen stood in Hangar 7 examining the captured aircraft, over 1,500 Mosquitoes had been built. They were appearing over Germany with increasing frequency, flying missions that seemed impossible. They photographed targets from altitudes and speeds that made interception nearly hopeless. They bombed with precision that heavy bombers couldn't match. They demonstrated that unorthodox thinking and creative use of available resources could produce results that conventional approaches couldn't achieve. The Luftwaffe needed to understand this wooden anomaly. They needed to know why it worked so well, whether its performance claims were real, and most importantly, how to stop it. The examination at Rechlin would provide answers. Some would be technical, others would be psychological. All would be uncomfortable for an Air Force that had believed it represented the pinnacle of aviation technology. The disassembly began on May 8, 1943. Petersen assigned his best technical specialists to the task, men who had examined captured British and American aircraft for years, who understood airframe design, aerodynamics, and power plant engineering. They approached the Mosquito with methodical precision that German engineering culture demanded. Every component would be measured, weighed, tested, and documented. Nothing would be assumed. The first surprise came when technicians began removing inspection panels. Where they expected to find metal framework, the stringers, longerons, and formers that defined conventional aircraft structure, they found shaped wood. The fuselage was not a metal framework covered with wooden panels. It was wood throughout, engineered wood, laminated, and formed into a structure that required no internal skeleton. The outer skin was the structure. Chief Engineer Hedman Vera Bake ran his hand along the interior surface. The plywood was smooth, precisely fitted, with joints so tight they were barely visible. He knocked on various sections, listening to the sound. Solid, dense, the wood itself had been impregnated with resin, making it resistant to moisture and dramatically stronger than raw timber. He had expected crude in construction, perhaps adequate for a stopgap measure, but inferior to metal. What he found was sophistication. Thewing attachment points drew particular attention. In a metal aircraft, wings bolted to reinforced sections of the fuselage through heavy metal fittings that distributed loads into the structural framework. The Mosquito's wings attached through wooden joints reinforced with metal plates, but the primary load path went directly into the laminated wood structure of the fuselage. The wooden structure itself was carrying flight loads that would typically require metal. BK ordered stress analysis and materials testing. They needed to understand the strength characteristics. The Merlin engines were familiar territory. Rolls-Royce Merlin 21s, each producing 260 horsepower at 3,000 revolutions per minute. These were essentially the same engines powering Spitfire Mark Vs, which German pilots respected as formidable opponents. The Mosquito had two of them, giving combined power of approximately 2,500 horsepower. For an aircraft this size, wingspan 54 feet 2 inches in, length 40 t 6 in, the power-to-weight ratio was exceptional. Technicians weighed components as they removed them. The fuselage structure came in far lighter than an equivalent metal airframe would weigh. Wood strength-to-weight ratio, when properly engineered, matched or exceeded aluminum in many applications. But wood offered another advantage. It didn't require the massive stamping presses, extrusion equipment, and specialized tooling that metal construction demanded. The British were building a high-performance aircraft using techniques that furniture makers understood. The absence of defensive armament became more understandable as the examination proceeded. Every gun turret added weight, drag, and complexity that a typical British bomber carried: multiple turrets, gunners, ammunition, and the structural reinforcement to handle recoil loads. All of that weight reduced speed and operational ceiling. The Mosquito carried none of it. The saved weight went into fuel, bombs, and additional speed. The entire design philosophy was different. Avoid the enemy rather than fight the enemy. Fuel capacity revealed another aspect of the design's sophistication. The Mosquito carried 545 imperial gallons in wing tanks and fuselage cells. 8 economical cruise settings, this gave range exceeding 1,500 m. The British could strike targets deep in Germany, photograph them, and return to England without the massive fuel loads that heavy bombers required. A Lancaster carried 2,400 gallons, but needed it to haul 7 tons of bombs with a 7-man crew. The Mosquito carried 1,400 pounds of bombs with a 2-man crew and achieved similar or better range with less than a quarter of the fuel. The bomb bay was compact but cleverly designed. 4 500 lb bombs could be carried internally, or a single 4,000 pounds blockbuster. The bombs were loaded vertically through doors in the belly, nested closely together. No complex racks, no heavy structural supports for external stores, everything was internal, minimizing drag. The bomb aimer's position in the nose gave excellent visibility for precision attacks, something heavy bombers struggled to achieve from high altitude. As examination continued through May, a picture emerged that troubled Petersen and his team. The Mosquito represented a fundamentally different approach to bomber design, one that achieved strategic effects through speed and altitude rather than defensive firepower and armor. More concerning, it achieved this performance using materials and construction methods that Britain could sustain indefinitely. Germany's bomber production was constrained by aluminum shortages and the competing demands of fighter production. Britain had apparently circumvented that constraint entirely. The captured Mosquito could not fly. The pilot had sabotaged the engines before capture, but the Luftwaffe had other ways to verify performance claims. Intelligence reports, combat encounter data, and mathematical analysis could reconstruct what the aircraft was capable of. Petersen assembled a team to collect every piece of information available about Mosquito operations over the previous 18 months. The reconnaissance variants like the captured PR Mark I had been particularly troublesome. These aircraft flew photographic missions over German-occupied territory and the Reich itself flying so high and so fast that interception was nearly impossible. The first recorded mission was in September 1941 when a Mosquito photographed targets in France. The aircraft flew at approximately 30,000 foot higher than most German fighters could effectively operate and at speeds exceeding 315 ft at that altitude. Fighter command records showed dozens of attempted interceptions. The pattern was consistent. Radar would detect an inbound target. Fighters would scramble, climbing hard to altitude. By the time they reached operational height, the Mosquito had already photographed its target and was accelerating away. The Bf-1009G could reach perhaps 370 miles per hour at 30,000 feet under ideal conditions, but it took time to accelerate, and the Mosquito already had a speed advantage. Pursuing fighters found themselves chasing a target that was pulling away. On December 6, 1942, Mosquitoes had photographed Berlin in broad daylight. The audacity was remarkable. Flying over the Reich capital, photographing government buildings and industrial facilities, then escaping before effective response could be organized. Goering had been furious. The mission proved that Britain could strike anywhere in Germany with relative impunity, at least with fast reconnaissance aircraft. What was photographed today might be bombed tomorrow. The bomber variants were equally problematic. Mosquito bombers had conducted nuisance raids on Berlin throughout the spring of 1943, timed to disrupt sleep and force civilians into shelters. The psychological impact was significant. German civilians who had been told the Luftwaffe controlled the skies heard air raid sirens nightly as fast British bombers struck and escaped. The raids didn't cause massive damage. A handful of aircraft carrying a ton or so of bombs, each couldn't match the destruction of a heavy bomber stream, but they demonstrated vulnerability and kept the population anxious. More concerning were precision strikes. On January 30, 1943, Mosquitoes had attacked Berlin during a scheduled daylight speech by Goering, forcing him to postpone the broadcast. On September 30, 1942, Mosquitoes struck Gestapo headquarters in Oslo, Norway with remarkable precision, destroying German records while minimizing Norwegian civilian casualties. These were not terror attacks or area bombing. These were surgical strikes using speed and accuracy instead of miss. Petersen reviewed combat reports from experienced fighter pilots. Oberleutnant Hans Mehr, flying a Bf-1009 out of Baden, had encountered a Mosquito on February 14, 1943. He had climbed to engage, reaching 28,000 feet where his aircraft was near its performance limit. The Mosquito was already at 32,000 feet. Mehr pushed his engine to emergency power, closing the altitude gap slightly, but the Mosquito simply accelerated. Mehr's combat report was blunt. Target maintained speed advantage throughout engagement. Unable to Classido firing range, broke off pursuit duetto fuel state. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us and continue producing in-depth content like this. Another pilot, Major Joseph Priller, one of the Luftwaffe's most experienced fighter leaders, had written an assessment in March 1943. Priller commanded Jagdgeschwader 26, an Allied unit stationed in France. His fighters regularly encountered Mosquitoes crossing the Channel. His assessment was damning. The British Mosquito bomber and reconnaissance aircraft represents a serious threat that current fighter tactics cannot effectively counter. The aircraft speed at altitude exceeds our intercept capability. Recommendation: develop dedicated high-altitude interceptor or accept that mosquitoes will operate with relative impunity. The Focke-Wulfs 190, Germany's other frontline fighter, fared no better. The FAU-190 had excellent performance at low and medium altitudes, but above 25,000 feet it lost effectiveness. The engine supercharger couldn't maintain power in thin air. Mosquitoes typically operated above that altitude when flying reconnaissance missions or when penetrating defended airspace. German fighters below them could see beacon trails but couldn't reach the aircraft making them. Some pilots reported success against mosquitoes at lower altitudes, particularly when the British aircraft were operating in ground attack or night fighter roles. In these scenarios, the mosquito wasn't necessarily trying to run. It was maneuvering to engage German targets, but reconnaissance and bomber variants flew high and fast, and interception success was rare. Intelligence estimates suggested that fewer than 5% of mosquito sorties over German-occupied territory resulted in successful interception. The British were losing mosquitoes primarily to accidents, weather, and mechanical failures, not to German fighters. The implications were uncomfortable for Petersen and the Luftwaffe leadership. Germany had invested enormous resources into developing advanced fighter aircraft. The Bf 1009 had evolved through multiple variants, each incorporating lessons from combat, each pushing performance higher. The Tupolev U-190 had been designed from the beginning as a modern fighter using the latest engineering knowledge. Germany had pioneered jet aircraft development with the Me-262 beginning flight testing. German aviation engineering was supposed to be the world's finest. And yet Britain had built a wooden aircraft that German fighters couldn't catch. The psychological impact went beyond mere performance comparisons. The Mosquito challenged fundamental assumptions about modern warfare and industrial competition. German military doctrine emphasized advanced technology and precision engineering. The Reich's propaganda constantly reinforced themes of German technical superiority. German workers were told they were building the world's finest weapons. German soldiers were told they fought with better equipment than their enemies. The Mosquito suggested that clever design and efficient use of available resources might matter more than technological sophistication. Britain wasn't trying to out-engineer Germany. Britain was using wood and material available in every forest to create aircraft that Germany's advanced metal fighters couldn't intercept. The strategic implications were profound. If wooden aircraft could achieve such performance, what other assumptions about modern warfare might be wrong? Petersen drafted his report in late May 1943. The document was technical, detailed, and as objective as possible given the uncomfortable conclusions. The Mosquito's performance claims were accurate. The aircraft could indeed exceed 400 miles per hour at altitude. It could operate above 30,000 feet. Its range allowed deep penetration into German airspace. Most critically, current Luftwaffe fighters could not reliably intercept it. The report included recommendations. Germany needed to develop high-altitude interceptors capable of sustained performance above 30,000 feet. Improved superchargers or turbochargers were essential. Alternatively, jet fighters like the Mi-262 might provide sufficient speed advantage to catch mosquitoes if the jet program could be accelerated and made reliable. Ground-based solutions improved radar, better coordination between detection and interception. Positioning fighters at altitude before mosquitoes arrived might help, but would be difficult to implement effectively across all of occupied Europe. The report went up the chain of command. Senior officers read it with varying reactions. Some acknowledged the problem and supported developing countermeasures. Others resisted conclusions that implied German technical inferiority. The political atmosphere in the Third Reich made it dangerous to suggest that the enemy might have advantages even when evidence was overwhelming. Goering in particular was known to react badly to reports suggesting Luftwaffe inadequacy, but reality couldn't be denied indefinitely. Mosquitoes continued operating over Germany throughout 1943 and into 1944. They photographed targets, bombed Berlin, and demonstrated that fast, unarmed aircraft could survive in defended airspace through speed alone. German aviation designers began work on advanced interceptors, but development took time and resources were increasingly constrained as the war situation deteriorated. For German pilots, the Mosquito became a symbol of frustration. They could see them, track them on radar, attempt interception, and watch helplessly as the British aircraft accelerated away. The psychological impact was corrosive. If Germany's fighters couldn't catch a wooden British bomber, what did that say about German technical superiority? What did it say about the war's likely outcome? The examination at Rechlin had provided answers to technical questions. It had verified performance. It had explained construction methods, but it had also forced a reckoning with uncomfortable truths. Sometimes unconventional approaches worked better than conventional wisdom suggested. Sometimes resource constraints drove innovation that technological advantages couldn't match. Sometimes the enemy was more clever than you wanted to admit. The wooden wonder had proven all of these lessons, and the Luftwaffe had no effective response. The Mosquito's dominance only intensified as 1943 progressed into 1944. The aircraft that Petersen had examined at Rechlin represented early production standards. Later variants incorporated improvements that made an already difficult interception problem nearly impossible. The BA-116 bomber variant entering service in late 1943 featured pressurized cabins allowing crews to operate comfortably at extreme altitudes. The FB Mark VI fighter bomber variant added 4 20mm cannons and 8 rockets, transforming the Mosquito into a devastating ground attack platform while maintaining its speed advantage. Production numbers told their own story. By the end of 1943, de Havilland and associated manufacturers were producing over 200 Mosquitoes monthly. British factories that had made furniture were now building combat aircraft at a rate that strained German intelligence analysts' credibility. How could Britain sustain such production using wood? The answer lay in resource allocation that Germany couldn't match, while the Reich struggled with aluminum shortages, competing demands from fighter and bomber programs, and the need to disperse production facilities away from Allied bombing. Britain's Mosquito production used entirely separate supply chains. The timber came from Canadian forests, shipped across the Atlantic despite U-boat threats. The balsawood core material came from Ecuador, transported through supply routes that German submarines couldn't effectively interdict. British furniture factories employed craftsmen whose skills were irrelevant to metal aircraft production but perfectly suited to Mosquito construction. Women who couldn't perform heavy metal work excelled at the precise woodworking that Mosquito construction required. The whole production system existed parallel to conventional aircraft manufacturing, adding capacity rather than competing for it. Mosquito operations expanded into roles the aircraft's designers hadn't originally envisioned. The night fighter variants equipped with airborne radar proved devastating against German bombers attacking British cities. The Mosquito's speed allowed it to catch bombers, and its heavy cannon armament destroyed them efficiently. German bomber crews who had terrorized British civilians during the Blitz now found themselves hunted by an aircraft they couldn't escape. The psychological tables had turned completely. Pathfinder squadrons used Mosquitoes to mark targets for heavy bomber streams. Fast Mosquitoes would arrive first. identify targets visually or by radar, drop colored markers, then escape before the main bomber force arrived. The technique dramatically improved bombing accuracy. German defenders had to choose between engaging the Pathfinder's fast aircraft that were difficult to intercept or waiting for the main bomber stream. Either way, the Mosquitoes made the heavy bombers more effective. Perhaps most galling for the Luftwaffe were the light bomber raids. Small formations of Mosquitoes, sometimes as few as 4 aircraft, would strike targets across occupied Europe and Germany itself. They bombed railway junctions, industrial facilities, and administrative centers with precision that heavy bombers couldn't match. The damage from individual raids was modest, but the cumulative effect was significant. More importantly, the psychological impact was profound. German air defenses, which had been built to counter massive bomber formations, struggled to engage small, fast targets that could strike anywhere. On January 30, 1944, Mosquitoes executed perhaps their most audacious mission. That morning, 18 aircraft from 140 Squadron attacked Amiens prison in occupied France. The objective was surgical precision, break through the prison walls to allow French resistance members to escape while minimizing casualties among prisoners. The Mosquitoes attacked at low altitude, bombing with remarkable accuracy. The walls were breached. The guards' quarters were destroyed. Over 250 prisoners escaped, including many resistance fighters scheduled for execution. The raid demonstrated capabilities that conventional bombers simply couldn't achieve: precision, speed, and daring combined in a single operation. German fighter development struggled to respond. The Focke-Wulfs TR-152, designed partly to counter high-altitude threats, wouldn't reach operational service until late 1944, and production numbers remained small. The Messerschmitts 262 jet fighter had the speed to catch Mosquitoes, but mechanical reliability problems and fuel shortages limited its effectiveness. Even when the 262s did intercept Mosquitoes, the jet's limited endurance meant brief engagement windows. By mid-1944, the Luftwaffe had essentially accepted that Mosquitoes would operate with relative impunity over German airspace. Fighters were increasingly reserved for engaging heavy bomber formations where interception had better success rates. The Mosquitoes' success forced uncomfortable questions about military procurement and industrial strategy that extended far beyond one aircraft type. Germany's aviation industry had pursued technological excellence through increasingly complex resource-intensive designs. Each new fighter variant incorporated advanced features, pressurized cockpits, sophisticated weapons systems, powerful engines requiring exotic materials. These aircraft were formidable when they worked, but they were difficult to build, maintain, and operate. Production numbers suffered because each aircraft required extensive specialized labor and materials. Britain's approach with the Mosquito was philosophically different. Rather than pursuing maximum technological sophistication, de Havilland had optimized for performance achievable with available resources. The result was an aircraft that performed better than competitors in many mission profiles while using materials and manufacturing techniques that Britain could sustain indefinitely. The strategic wisdom of this approach became apparent as the war continued and Germany's resource situation deteriorated. By 1944, German industry was producing remarkable aircraft. The TAR-152, the Me-262, the He-219, but in numbers too small to affect the war's outcome. 100 advanced fighters couldn't defend the Reich when thousands of Allied aircraft filled the skies. Meanwhile, Britain was building Mosquitoes by the hundreds monthly using resources that didn't compete with Spitfire, Lancaster, or other aircraft production. The Mosquito added capability that Germany couldn't match because Germany had no equivalent resource pool to draw from. The psychological impact on German military leadership was corrosive. Petersen's report from May 1943 had warned that the Mosquito represented a serious threat requiring dedicated countermeasures. Those countermeasures never materialized in effective form. The Luftwaffe's response to the Mosquito threat was essentially to accept it and focus resources elsewhere. This acceptance represented a profound shift from the early war confidence that German engineering would prevail through technical superiority. German pilots who had flown against mosquitoes, those who survived the war to tell their stories, consistently described a sense of futility. They could see the enemy, could attempt interception, could even occasionally engage at disadvantageous ranges, but they couldn't prevent the mosquitoes from accomplishing their missions. Major Heinz Wolfgang Schnaller, the Luftwaffe's most successful night fighter pilot with 121 confirmed victories, described the Mosquito as the aircraft we most feared, despite having shot down several himself under favorable circumstances. When the enemy you most feared was made of wood and plywood, what did that say about your own technological advantages? The post-war analysis conducted by Allied intelligence teams examining captured German documents revealed the extent of Luftwaffe frustration. Internal memos from Goering's staff showed repeated demands for solutions to the Mosquito problem. Aircraft designers responded with proposals for high-altitude interceptors and jet fighters. But proposals required time to develop, resources to build, and operational and circumstances to deploy effectively. Germany had none of these in sufficient measure. By late 1944, the Reich's industrial capacity was crumbling under Allied bombing, resources were critically short, and experienced pilots were increasingly scarce. The Mosquito flew its final combat missions in May 1945 as the war in Europe ended. The aircraft had been produced in over 30 major variants, serving in roles from high-altitude reconnaissance to anti-shipping strikes. Total production exceeded 7,800 aircraft built in Britain, Canada, and Australia. Operational losses were remarkably low for an aircraft that flew in combat throughout the war. The speed and altitude performance that made interception difficult also made survival likely. German records captured after the war showed that Mosquito loss rates over German-occupied territory were approximately 3% of sorties flown compared to 5 to 8% for heavy bombers during the same period. The Mosquito's design philosophy, speed as survival, had been vindicated by operational results. The aircraft proved that unconventional solutions could outperform conventional approaches when design priorities aligned properly with operational requirements and industrial capabilities. Oberst Edgar Petersen survived the war. He was captured by American forces in May 1945 and spent 2 years in detention before release. In post-war interviews, he spoke candidly about the Mosquito examination at Rechlin. He acknowledged that the aircraft had challenged his assumptions about aviation engineering and modern warfare. He admitted that Germany's response to the Mosquito threat had been inadequate, hampered by resource constraints, competing priorities, and an institutional reluctance to acknowledge that the enemy might have designed something genuinely superior in certain respects. The de Havilland Mosquito remained in service with various air forces until the 1950s. The Royal Air Force retired its last operational Mosquitoes in December 1955. The aircraft had served for 14 years, a remarkable lifespan for a design that critics had initially dismissed as obsolete before it flew. Several air forces continued operating Mosquitoes into the 1960s for specialized roles. The Israeli Air Force flew Mosquitoes during the 1948 Arab-Israeli War. The Dominican Republic operated them into the mid-1950s. The aircraft's basic soundness and performance longevity validated de Havilland's unconventional approach. Modern aviation historians studying the Mosquito consistently identify it as one of World War II's most successful aircraft designs when measuring performance against production cost, operational effectiveness, and strategic impact. The aircraft cost approximately half what a Lancaster bomber cost to build, flew missions the Lancaster couldn't attempt, and survived at higher rates. It demonstrated that creative engineering using available resources could produce results that brute force technological development couldn't match. The Mosquito's influence in post-war aviation design was subtle but significant. The aircraft proved that multi-role capability had genuine value. A single airframe serving effectively in reconnaissance, bombing, night fighting, ground attack, and anti-shipping roles. Simplified logistics and training. Later multi-role aircraft like the F-4 Phantom in American service or the Tornado in European service owed conceptual debts to the Mosquito's operational flexibility. More importantly, the Mosquito validated the principle that operational requirements should drive design choices rather than technological fashion. In an era when all-metal construction was considered modern and advanced, de Havilland chose wood because it better served his objectives. The decision was pragmatic rather than ideological. The result was an aircraft that performed brilliantly in its intended roles and adapted successfully to roles never initially envisioned. For the Luftwaffe pilots who faced Mosquitoes, the aircraft represented a turning point in their understanding of the war. Early in the conflict, German pilots had believed their equipment and training gave them decisive advantages. Encountering enemies they couldn't catch, couldn't shoot down, couldn't prevent from completing their missions eroded that confidence. The Mosquito wasn't the only factor in this psychological shift. Allied numerical superiority, improving Allied tactics, and deteriorating German circumstances all contributed, but it was a particularly visible symbol of how technological assumptions could be wrong. The captured Mosquito, examined at Rechlin in May 1943, remained in German hands until the war's end. It was eventually recovered by British forces and returned to the United Kingdom. Several Mosquitoes survive today in museums worldwide. The de Havilland Aircraft Museum in England preserves the prototype that first flew in November 1940. The Royal Air Force Museum displays multiple variants. The Canadian Warplane Heritage Museum operates a flying example. These preserved aircraft allow modern viewers to examine the construction techniques that confounded German engineers 8 decades ago. Standing beside a Mosquito today, you can knock on the fuselage and hear that hollow sound just as Petersen did in Hangar 7. You can see the wooden construction, the elegant lines, the compact bomb bay, the absence of defensive armament. The aircraft looks deceptively simple. That simplicity was deliberate, the result of careful design choices that prioritize practical effectiveness over technological complexity. The story of the Mosquito and its impact on the Luftwaffe remains relevant as a case study in how military organizations respond to unexpected challenges. When your assumptions prove wrong, when the enemy succeeds with methods you dismissed as obsolete, adaptation requires intellectual honesty and institutional flexibility. The Luftwaffe possessed neither in sufficient measure. They recognized the problem, understood its implications, but couldn't adapt effectively because their entire industrial and doctrinal structure was committed to different approaches. That morning in May 1943, when Petersen watched technicians uncover the captured Mosquito, he witnessed more than just an examination of enemy equipment. He witnessed the collision between assumption and reality, between what his experience told him should be true and what the evidence proved was actually true. The wooden aircraft before him hadn't have worked. Everything Heck knew about modern aviation said that metal was superior, that defensive armament was necessary, that bombers needed armor and gunners to survive. But the Mosquito worked brilliantly. It worked because its designers had asked different questions, made different assumptions, and optimized for different priorities. It worked because Britain's strategic situation demanded creative solutions that conventional thinking couldn't provide. It worked because sometimes the unconventional answer is the right answer regardless of what prevailing wisdom suggests. The Luftwaffe examined the Mosquito, understood its capabilities, acknowledged its effectiveness, and then proved unable to counter it. That inability reflected not individual failures but systemic constraints, industrial, strategic, and institutional, that Germany couldn't overcome. The wooden wonder remained uncatchable, not because German engineers lacked skill or German pilots lacked courage, but because Germany had committed to an approach that couldn't adapt to what Britain had created. 8 decades later, the lessons endure. Technological sophistication doesn't guarantee success. Unconventional approaches sometimes produce better results than conventional. Wisdom predicts. Resource constraints can drive innovation that abundance cannot. And sometimes the enemy surprises you with something that shouldn't work but does, and all you can do is acknowledge the reality and wish you had seen it coming. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now.